A FriedelCrafts acylation works a lot like a FriedelCrafts alkylation. Remember, in a FriedelCrafts alkylation, the alkyl group is just any carbon group, any carbon chain. And you'd have that bonded to some sort of leaving group like a chlorine. And you use that with like a metal catalyst to form a really good electrophile, the carbocation that we saw in the mechanism for FriedelCrafts alkylation. An acyl group, though, an acyl group is a carbon chain, but at the end of the carbon chain you have that carbon to oxygen double bond. Now in this case we're going to take that acyl group and we're going to bond it to the chlorine just like before, and you'll see the mechanism is almost exactly the same. The difference that acyl group will make is that you won't get carbocation rearrangement. The double bond to the oxygen will have a resonance form that stabilizes the positive charge on that carbon. And so if you're trying to form a bond to benzene, let's say for example you wanted to put a propyl group on benzene, you would not be able to do it through Friedel-Crafts alkylation, because you would form a carbocation, you would form this primary carbocation, and that would rearrange to the more stable secondary carbocation. So you'd end up adding an isopropyl group to the benzene. So it would look like that. So if you want to put a primary carbon on a benzene ring and not have to worry about carbocation rearrangement, then you want to use Friedel-Crafts acylation. So that's sort of the reason why you're learning the second way to make this carbon-to-carbon bond onto a benzene ring. And the other thing, of course, is sometimes you may want the carbon-to-oxygen double bond. So this mechanism will look really familiar. The only difference is this carbon-to-oxygen double bond and the stability that it gives the carbocation that you form. Otherwise, the R can be any group. So in this case, the R happens to be 2 carbons there. It says, draw the mechanism for the following reactions. Well, it's going to be, first, you have your metal catalyst, like we've seen in Friedel-Crafts alkylation, and we also saw a metal catalyst in bromination. And the metal, anytime you see a metal in organic chemistry, you should think really low electronegativity. So it loses its electrons, becomes slightly positive. And everything it's bonded to is stealing those electrons, so that becomes slightly negative. Now this is a trigonal planar molecule. That aluminum is bonded to 3 atoms and 0 lone pairs, so that's trigonal planar. It's flat like a pancake. When the chlorine can descend on top of it, like a fist onto a pancake. And when that happens, all the electrons rush to the side, because chlorine is very big, so it's very polarizable. So all the electrons rush to the side where the positive aluminum is. And that side becomes slightly negative and really nucleophilic. That's in addition to the bond dipole that you already have, where the chlorine is slightly negative. So those two effects, the polarizability of chlorine and the slightly negative charge from the bond dipole, both of those act together to make this chlorine act as a nucleophile and attack the aluminum. So this should seem really familiar from Friedel-Crafts alkylation so far. So once you have that, you form this next intermediate. Now the aluminum is forced to have a lot of electrons around itself, more than it can handle. It has that full negative charge. The chlorine is sharing to more of its electrons than it would like to, so it has that full positive charge, and this molecule crumbles apart. Now it can crumble apart in a couple ways. The chlorine, first of all, is really electronegative, and it has a full positive charge, so it's going to steal electrons from somebody. It could steal electrons from the aluminum, in which case you just get your original reactants. That's why you have this equilibrium here. That wouldn't get the reaction anywhere. The way you can get something different is if the other electrons go onto the chlorine. And in that case, you end up getting 2 intermediates. On the one hand, you have this carbon that has now lost electrons, and so has a positive charge. And then you get that metal catalyst intermediate. Unstable, because you're forcing a negative charge on on an atom that has very low electronegativity. It's unable to hold on to negative charge. But this is the special thing. This is why Friedel-Crafts acylation is different from Friedel-Crafts alkylation. In Friedel-Crafts alkylation, we wouldn't have this carbonyl, and so the carbocation would rearrange. Its primary would go right next door and become secondary. Oops. But here, instead, it forms a resonance structure. It's actually stabilized through resonance. One of the 5 resonance patterns that you learned in Organic Chemistry 1 is that if you have a lone pair next to a positive charge, you get another resonance structure where the lone pair goes toward the positive charge to help to stabilize it. And so you have this one resonance structure combined with this other one. So I'll draw that carbon in. Now we're going to have 3 bonds, so this is going to be linear. This carbon still has, that carbon, actually, its positive charge will be stabilized, but now the oxygen will have a positive charge. So that ion is called an Acelium Ion. You notice it's happening because you have the acyl group there, the carbon double bonded to an oxygen. And so this ion is called an Acelium Ion, and it stabilizes that positive charge. That's stabilized through resonance, so the carbocation doesn't rearrange. Okay, so our Acelium Ion. Well, that's an awesome electrophile. It has a full positive charge, and so the benzene can now swoop in. Let's just keep track of this one hydrogen there. It'll swoop in and attack that very intense electrophile. So we end up getting the benzene ring, and now we have the carbonyl there and the 3 carbons attached, right? 1, 2, 3. We still have the hydrogen, and the electrons have gone to form that new bond. So those electrons, these electrons have gone to form this new bond. And the carbon on the right there has just lost them, so it only has a positive charge. And we've seen this many times before in bromination, sulfonation, nitration, and Friedel-Crafts alkylation. That positive charge there, that carbocation, is an empty p orbital that's parallel to the 2 p orbitals responsible for the pi bond, and so the electrons spread out, and you express that spreading out through resonance, or drawing resonance structures. So you put brackets to warn people none of these structures are the true structure, only the average of them all is the true structure, and you draw those special resonance arrows that tell people take the average. When you have this allylic positive charge, that's a positive charge that's 1 atom away from an atom in a double bond, the pi bond goes toward the positive charge to help stabilize it. And so the next resonance structure has the pi bond on the right, and now the carbon that's missing the electrons is the one at the bottom. It had pi electrons in the previous structure, now it doesn't, so it has that positive charge. This is now allylic to the other pi bond, and so you can express the electrons in that pi bond flowing into that parallel p orbital there by moving them toward the positive charge. Oops. And you draw that resonance arrow that's telling people to take the average of these structures, and you end up with this carbocation there, the positive charge there. And so this is your resonance-stabilized intermediate. Remember, that's called the sigma complex. When you destroy aromaticity by adding a strong electrophile, but it's stabilized through resonance, that's your sigma complex. And it's relatively stable because of the resonance, but you destroyed the aromaticity. The molecule would really like the aromaticity back. And we also have this other feature. All of the bonds here are repelling each other. They want to push each other off the molecule. Aluminum is a metal. It has very low electronegativity. It's not able to hang on to those. And so one of the chlorines takes its electrons, steals the hydrogen, and those electrons that were keeping the hydrogen on the benzene go to reform the aromaticity. So you end up with your benzene ring with its aromaticity back, but now you have this acyl group attached to it. You also have the HCl, which isn't that important, and you have AlCl3, which is important because it's a catalyst. So it's important that if you start with it, you should get it at the end. And that shows that it's not being used up, it's just helping the reaction to happen, so it's a catalyst. And that's it. That's the mechanism for Friedel-Crafts acylation. You have this acyl group here now. It's useful to know that there is one recipe. You can reduce this. If you ever turn bonds to oxygen into bonds to hydrogen, that's reduction. In general, if you turn bonds to electronegative atoms into bonds to hydrogen, it's called reduction. And you can reduce these acyl groups that you get after this Friedel-Crafts acylation. If you don't want them, you can reduce them by adding a zinc mercury amalgam. So you take zinc and mercury metal and you smush them together until they become like this new Frankenstein metal. And then you combine that with HCl, and that ends up reducing them. So you end up getting just the chain. So it's a useful thing to know how to do, this little trick there, that little recipe. That's how you can form those bonds between a benzene ring and a primary carbon using this Friedel-Crafts acylation. And sometimes you may want the acyl group on there. You'll notice this is a ketone, and maybe you want a ketone. So I'm going to quickly go through that same mechanism one more time, but I'll do it really fast, just because just because we've seen it so many times before. And it's really the same thing as what we just saw. Okay. So, let's just make some space. All right. So, first step, we need to create an awesome electrophile. And we do that using these two things on the right. Notice this is exactly the same as the last one. The only difference is the chain, the carbon chain. It looks a little more confusing, but remember that carbon chain was not involved in the reaction at all. It just was along for the ride. So here we can take this weird looking carbon chain and when that'll get close to this metal catalyst. Remember, in the metal catalyst, the chlorines are slightly negative. They're stealing electrons from the very low electronegativity aluminum atom. The chlorine has a slightly negative charge to begin with because it's electronegative, stealing them from the carbon. Plus, it's very polarizable, so all of its electrons go to the side that's facing the aluminum. It attacks the aluminum, and you get this first intermediate. Again, the carbon chain is just there for the ride. It stays the same. Chlorine is bonded to the aluminum. Oops. And then You have each of those chlorines there. The aluminum has a full negative charge. The chlorine has a positive charge. So it's a really unstable intermediate. It wants to crumble and break apart. It could break apart in two ways. The chlorine, which is very electronegative and trying to stabilize a positive charge, could just snap these electrons away from the aluminum, and we end up back with our reactants. That's why you have this equilibrium here. Oops. That's one way, but there is another way that this can crumble apart, and that is if the electrons on the other side of the chlorine go onto it. So in that case, you end up with two intermediates. Oops. You end up with the carbon involved in the carbonyl with a positive charge, and then you end up with this metal bonded to 4 chlorines. And they're both pretty unstable, but this molecule on the left is able to form a resonance structure because you have lone pairs next to a positive charge. And that, oops, let me just bring that down here. Lone pairs next to a positive charge, that's one of the 5 resonance patterns. Those lone pairs can go toward the positive charge. I'm going to put these in brackets. Use the resonance arrow to tell you that the true structure is only the average of the 2. That carbon there will be triple bonded to the oxygen, and I'm drawing it in a straight line because remember, if an atom has 2 atoms on each side and no lone pairs, it's linear. So the carbon doesn't have a positive charge anymore, but the oxygen does. And so that's the resonance structure. That's our Acelium ion. And that's the awesome electrophile that benzene can swoop down and attack. Oops. So benzene can come in, weak nucleophile that it is, and attack that awesome electrophile. And the advantage here to using this Friedel-Crafts acylation is this resonance structure. That resonance structure stabilizes this carbocation and prevents it from rearranging. This is a primary carbon. That carbon is only bonded to one other carbon, and this right next door to it would be a tertiary carbon. So if this were Friedel-Crafts alkylation, the carbocation would move over, and the benzene ring would attack here. But because it's Friedel-Crafts acylation, it stays where it is. It's stabilized by the resonance of the Acelium ion, and you end up getting attack at the very end of the primary carbon. So once you get that attack, you have this benzene ring. So that's our benzene ring. If you ever get confused when drawing things, you can always number them. So like 1, 2, 3, 4. We have 1, 2, 3, 4. Notice we have methyl groups off of 2 and 3, methyl groups off of 2 and 3. Okay, so we're left with this. However, remember there's this hydrogen already here, that hydrogen is there, and the electrons you use to attack the Acelium ion, those electrons here go to form this new bond. And so they have left this other carbon in the dust, and that has a full positive charge now. But as we've seen so many times, that positive charge is allelic to the pi bond, and so you end up getting resonance. So you have the brackets that warn the world that all the true structure is not any of these individual structures, it's only the average of them. And when you have an allelic lone pair, the pi bond goes, an allelic positive charge, the pi bond goes toward the positive charge. And that's how you can draw your next resonance structure. So in that case, the pi bond goes to the right. You get your positive charge at the bottom. That positive charge, though, is now allylic to the other pi bond, so it spreads out that way. And whenever you're drawing the resonance structure, the pi bond goes toward the positive charge to form a new bond. And so you get this third resonance structure where the positive charge is neutralized by those electrons, but that leaves a positive charge in the top left. So these three resonance structures that make up your sigma complex, that's that resonance stabilized complex that helps lower the energy that you need to make the reaction happen. And once you've got that, you just want to restore aromaticity. You need a base, and we're going to use this base that we have here, our catalyst. All of the electrons in these bonds are pushing each other apart. Aluminum is not electronegative, so it's not really able to hold on to them. And one of the chlorines comes off, steals the hydrogen, and the electrons going to the hydrogen snap back into the ring to create aromaticity. So you end up with the benzene ring now with its aromaticity back. You have your acyl carbon chain. You have the chlorine that was kicked off of the aluminum combining with the hydrogen, so hydrochloric acid. And you have the aluminum catalyst back, AlCl3. So you ended up, you can think of this in two ways. You ended up putting this acyl group on the benzene. That's one way you can think of it. The other way you can think of it is you replaced the chlorine with a benzene ring. You added a benzene ring onto what was the acyl chloride. So that's Friedel-Crafts acylation. It should seem very similar to you to Friedel-Crafts alkylation. The only difference is that you get that Acelium Ion, and that Acelium Ion helps to stabilize that carbocation intermediate so that you don't get carbocation rearrangement. So you're able to form carbon-to-carbon bonds from a benzene to a primary carbon. And that is the magical Friedel-Crafts